Now let's solve a few simple problems. The first question is this. Consider a state denoted by ket alpha or represented by ket alpha, which is expanded in the eigenbasis of an observable A as follows. Okay, so the ket is given and its expansion in terms of the eigenbasis of A is also given. So it's given by square root of 3 divided by 3 ket A prime plus 2 by 3 ket A double prime plus square root of 2 by 3 ket A triple prime. The eigenvalue equation is given as A acting on ket A prime is equal to A prime multiplied by ket A prime. This is the eigenvalue equation. This means that the kets here are represented by the corresponding eigenvalues. The eigenkets are represented using the corresponding eigenvalues. Okay, which means that, so according to our measurement theory that we discussed, if I measure the observable A on this state, okay, I'll get either A prime or A double prime or A triple prime. Okay, so let's assume that this is a three-dimensional space, which means that it's spanned by these three eigenkets. Okay, so it's a three-dimensional space. There are three basis vectors. Right? Now the question is this: what is the probability that immediately after measurement the system will be in the state ket A double prime? What's the probability that it will be in this state immediately after measurement? Okay, so we know that during a measurement the state of the system changes. Suppose you are measuring the observable A, it changes to one of the eigenkets of A. This is the basic measurement theory. So it changes either to ket A prime or to A double prime or to A triple prime. We don't know which. We don't know to which it's exactly going to change, but we can calculate the probabilities. Okay, so the question is, what's the probability that immediately after measurement the system will be in the state ket A double prime? So what's the probability that this change happens from alpha to ket A double prime? That's the question. Now we know that the probability that it changes to ket A double prime is given by, for that you first calculate the coefficient of ket alpha in the direction A double prime. Okay, calculate the coefficient of ket alpha in the direction A double prime and then modulus square it. This would be the probability given the state is normalized, given that the state is normalized. Okay, so let's check for normalization anyway. First let's check for normalization. Let's check if the state is normalized. Okay, let's check if the state is normalized. So we'll do it this way. If the state is normalized, that means that bracket alpha alpha is equal to 1. Bracket alpha alpha is equal to 1. That can be checked easily. Let's do this anyway, right? Let's do all the steps so that these things become clearer. Later on, we can do it in an easier way, which I'll explain. So let's first, we have given ket alpha is given here. Let's find bra alpha. Let's do it in the next slide. So let's check for normalization. Is this combination bracket alpha alpha, is this equal to 1? So let's do it like this. First, let's find the ket alpha is given here. Let's find bra alpha. Okay, bra alpha is actually, so we know that when you go from ket space to bra space, the numbers have to go into their complex conjugates, right? But here all we have are real numbers. Okay, so the complex conjugation doesn't change it. Anyway, let's write it like this. So this becomes root 3 by 3 star, and then I've got bra A prime plus 2 by 3 star, and I've got bra A double prime plus root 2 by 3 complex conjugate bra A triple prime. Bra A triple prime. Okay, now we just need to combine bracket alpha alpha. Right, so let me write bra alpha first. This is root 3 by 3 bra A prime plus 2 by 3 bra A double prime plus root 2 by 3 bra A triple prime. Okay, multiplied by ket alpha. Ket alpha I'll write here. It's root 3 by 3 ket A prime plus 2 divided by 3 ket A double prime plus root 2 by 3 ket A triple prime. Okay, what we need to do now is to take each ket from this bracket, all right, and then combine it with every ket here, right? Combine it with every ket here. This is what we need to do. So let's first take the first term here, root 3 by 3 bra A prime. Okay, I can combine it with this first term. Since this is a number, this root 3 by 3 is a number, I can take it out. All right, so the numbers will pass right through bras or kets. Okay, they don't make any change. It doesn't matter where we put the numbers. So we can combine the numbers first. So the first term becomes root 3 by 3 square. Alright. So if this is a complex conjugate, we'll normally write this as root 3 by 3 modulus square. Alright. So since these are complex conjugates, since we are dealing with real numbers here, I haven't written the complex conjugate symbol here. But generally this would be of the form root 3 by 3 square. Okay. So I've got root 3 divided by 3 square plus, sorry, and then I have to combine this bra with this ket here. Okay, that would give me bra a prime ket a prime, which is equal to 1 by orthonormality. Right? We assume that we are dealing with an orthonormal basis, unless otherwise specified. Right? So if nothing else is given, we'll assume that we are dealing with an orthonormal basis. Okay, so this is 1. Okay, plus I have to combine this bra. Right, I have to combine this bra with the second ket here. Okay, so in this case we know that the combination bra a prime ket a double prime is actually 0, again by orthogonality. Right, so the bra a prime ket a double prime is actually 0 by orthogonality. So we just, so this term has no contribution. We have to combine this with the third term also, again that term goes to 0 by orthogonality. Okay, so this means that we need to combine bra a prime only with ket a prime, all other terms are 0. Now again we take the second term here, 2 by 3 bra a double prime. Again in principle I have to combine it with all the kets here. Okay, but when I combine bra a double prime with ket a prime, that is 0, again by orthogonality. Bra a double prime with ket a double prime, that's 1. So I get 2 by 3 square. Alright, and plus the third one. Alright, the third bra I have to combine with all of them, but again the non-zero combination is bracket a triple prime. Is that also, this bracket a triple prime is also 1, all other terms are 0. So we have got root 2 divided by 3 square. Okay, what is this? This is equal to, let's square each term. This is 3 divided by 9 plus 4 divided by 9 plus 2 divided by 9, which is simply 9 by 9 and is equal to 1. So the state is normalized. The state is normalized. Okay. Now, if you look here, we didn't have to do all these steps, all right? Just by making use of the fact that we have written the multiplication here, and then we have done every term, all right? But we don't have to do that if the basis is orthonormal. What we have done here is simply we have taken each expansion coefficient here, all right, squared them and added them, all right? So the condition for orthonormality, or sorry, the condition for what do you say, normalization of the vector. Okay, the condition for normalization of the vector is that you just take the modulus square of each expansion coefficient, all right, and add them and check if this is equal to 1. If this is equal to 1, then we say that the state is normalized. Okay, so if the state, I repeat, if the state is expanded in a basis, all right, if the state is expanded in an orthonormal basis, that is, all right, if the state is expanded in an orthonormal basis like this, C1A1 plus C2A2 plus C3 A3, right? If get A1 A2 A3 etc. form an orthonormal basis, then the condition for normalization of the vector, the condition that the vector is normalized, is simply modulus C1 square plus modulus C2 square plus modulus C3 square equal to 1. All right, now we interpreted in quantum mechanics, we interpreted these modulus squares as the probabilities. So what is C1 modulus C1 square? This is the probability of measuring an eigenvalue a1. All right, this is the C2 modulus C2 square is the probability of measuring an eigenvalue a2, and modulus C3 square is the probability for measuring an eigenvalue a3. Sorry, yeah, I think we can write this a1, a2, a3. Right. So the normalization condition here. What does the normalization condition here mean? It means that, right, it means that the sum of the probabilities over all possibilities add up to 1. Okay? The sum of the probabilities over all possibilities, they have to add up to 1. Right? This is necessary for probability interpretation. Okay, so here the only possibilities are A1, A2 or A3, which means that if I measure observable A, right, if I measure observable A on alpha, right, by measurement theory, I will get either A or A prime or A triple prime. Sorry, A prime, A double prime or A triple prime. I'm sure to get either of these values. which means that the sum of the probabilities for each of these values have to add up to 1. So the condition that the ket is normalized, the given ket is normalized, also means that the sum of the probabilities over all possibilities add up to 1. Okay, so this is a normalized state. This is a normalized state. Okay. Now we need to find, what we needed to find is the probability that after measurement the state is ket A double prime. Right, so we are looking for the probability that on measuring observable A on the state ket alpha, what's the probability that it changes to ket A double prime? So measurement theory says that it will change to one of the eigenkets of observable A. All right, we are asking specifically what's the probability that it will change to ket A double prime. All right, now the probability interpretation or the postulate for calculating probability says that if ket alpha is normalized, which it is as we checked, right, then the probability that it will reduce, let's put it like this, the probability that ket alpha will change to ket A double prime, okay, is given by the projection. First you find the projection of ket alpha onto ket A double prime or onto a direction ket A double prime, and you take the modulus square. This is the probability that ket alpha changes to ket A double prime on a measurement of the observable A. So let's find this. You just take a bra A double prime on the left of ket alpha, and by orthonormality, bra A double prime ket A prime is 0, bra A double prime ket A double prime is 1. So I've got 2 by 3. Okay, and bra A double prime with ket A triple prime is also 0 by orthonormality or orthogonality. Okay, so if I want to find the probability, I have to take the modulus square of this expansion coefficient, right? So this is simply 4 divided by 9. Okay, that's the answer, right? Now maybe I'll uh, just explain a little bit further. All right, another way of saying is that, so if we say that the state has changed to ket A double prime, that means that the measured eigenvalue is A double prime. Okay, so these probabilities we can also call them like this. The probability of measuring A prime, an eigenvalue A prime, is given by modulus square of the projection of ket alpha onto the corresponding eigenket. Right, this is the projection of ket alpha in the direction of the corresponding eigenket, right, or the eigenket corresponding to the eigenvalue. Okay. So this is also the probability of measuring an eigenvalue A double prime or obtaining an eigenvalue A double prime as a result of my measurement. Okay. Similarly, I can say P of A double prime is equal to modulus of A double prime ket alpha square, that's what we calculated here, and P of A triple prime is equal to modulus square of this number. All right. So in general, if you are given the expansion of the ket in terms of the eigenkets of an observable, let's say C1A1 plus C2A2 plus C3 ket A3, all right, then the probability, let's suppose this is normalized, all right, assuming that the state is normalized, the probability of measuring A1 is equal to modulus C1 square. The probability of measuring A2 is modulus C2 square. The probability of measuring A3 is equal to modulus of C3 square. Right? This is how we calculate the probabilities. Probabilities are simply the modulus square of the expansion coefficients. Right? If the states are normalized, all right, if the states are normalized. So this mod C1 square can also be written as we did here, it also can be written as ket bra A prime ket alpha modulus square. Okay, so this is how we calculate the probabilities using the probability postulate in quantum mechanics. Okay. The second part of the question is to find the expectation value of A or the average value of A in this state. Right? Now the definition for the expectation value of A is bra alpha A ket alpha. So this is how you find the expectation value or the average value. Right. So this means that I could make measurements on a large number of identically prepared systems. All right, we have a large number of systems which are all exactly in the state ket alpha. Now I measure A on this state, I measure A on the second system, on this system, on the second system, on the third system, etc. I make this measurement on a large number of identically prepared systems. Okay, and each time I get one of the eigenvalues of A. Each time I get one of the eigenvalues of A. All right. Now the question is, what's the average value? What is the average value? All right. Now we know how to find the average value. So let's do it in two ways. All right. We could do it like this. We could do it like this. Or, okay, if we do like this, what we get is this. The average value is simply, let's write it like this. Average value of A is probability of A prime multiplied by A prime plus probability of A double prime multiplied by A double prime plus probability of A triple prime multiplied by A triple prime. Right? This is a standard definition for average value. Right? Because if you make a large number of measurements and you get n1 times a1, n2 times a2, n3 times a3, the average value is simply n1 a1 plus n2 a2 plus n3 a3 divided by the total number of measurements. Right? This is written as n1 divided by n a1 plus n2 divided by n a2 plus n3 divided by n a3. All right. Notice this n1 divided by n, it's a number of times, or it's a uh, fraction of times that you get the value a1. So this I can write as p of a1, and n2 by n is the what is experimentally measured or empirically measured probability. Right? The fraction of times you get the value a2. So this is p of a2, and n3 divided by n is p of a3. That's why we say that the average value is p of a1 plus p of a2 plus p of p of a double prime plus p of a triple prime a triple prime. Now we calculated each of the probabilities earlier. What's the probability that you'll get a prime? It's root 3 by 3 square, or modulus square of root 3 by 3. So let me write this as modulus square of root 3 by 3 square a prime plus what's p of a double prime? It's modulus square of 2 by 3 square plus root 2 by 3 modulus square of root 2 by 3. Sorry, here I have to multiply by a double prime modulus square of root 2 by 3 a triple prime. What is this? This is equal to, let's say, 3 divided by 9 a prime plus 4 divided by 9 a double prime plus 2 divided by 9 a triple prime. You add all of this, that will give you the average value or expectation value. All right. So if we know these numbers, we can just substitute it here and add them. That would be the average value. Right. Now we use the definition for averages here. Here we used the normal definition for average. You could also calculate the same thing by this. All right. This thing actually boils down to this. If we calculate this bar alpha a ket alpha, which is the definition for expectation value that we discussed, it again comes back to this expression for average value. Right. I'll just demonstrate it here so that it's clear. Okay, so in this case, if you have an expansion in terms of an orthonormal basis, if you need to find the average value, what you do is this. All right, what's p of a prime? The measurement theory says that it is modulus of c1 square. All right, what's p of a double prime? It's modulus of c2 square. What's p of a triple prime? It's modulus of c3 square. Sorry, square. All right. Okay. Now I just want to demonstrate that this expression boils down to this. We have seen this in the theory class, but I would like to explain it once again. Okay, so that there's no doubt that both these approaches are equivalent. Okay, it's exactly the same thing. This also will demonstrate that the expectation value defined like this, is indeed the average value. All right. So let's do this. Okay, we have got bar alpha equal to, this is something that we calculated before, root 3 by 3 bar a prime plus 2 by 3 bar a double prime plus root 2 by 3 bra a triple prime. Okay, so let's find bra alpha a get alpha. So first I write bra alpha here, root 3 by 3 bra a prime plus 2 by 3 bra a double prime plus root 2 by 3 bra a triple prime. Okay, and the operator A is sandwiched between bra alpha and ket alpha. Ket alpha again I write in terms of the eigenkets of operator A. Okay, so this is equal to root 3 by 3 ket a prime, okay, plus root it's 2 by 3 ket a double prime plus 2 by 3 ket a triple prime. Okay, so there's this curly bracket I have to close here. Okay, so that bracket is closed. Now I can use the eigenvalue equation. A acting on ket A prime is A prime ket A prime. Okay, so what I can do is that using the associative property of multiplication, I can choose to take this operator inside. I can choose to distribute it over this sum. Okay, so that would be, I write this as, this is equal to, I write this part as the same, root 3 by 3 bra A prime plus 2 by 3 bra A double prime plus root 2 by 3 bra A triple prime. Okay, now I take this A inside, right, and A acting on ket A prime by eigenvalue equation is, okay, we have the eigenvalue equation here, let me repeat, A acting on ket A prime is A prime ket A prime, that's the eigenvalue equation. Okay, so this A acting on ket A prime will give you A prime ket A prime. This is a number, so there's no problem, the operator will just move past the number. Right, the operator does nothing to this number, just moves past, and A acting on A prime can be written as A prime ket A prime. So this number is still there, so let me write it here, root 3 by 3 A prime ket A prime. Okay, now A goes here, and the number, it goes past the number, so I have got 2 by 3, and A acting on A double prime is the eigenvalue A double prime. Okay, now A acting on ket A triple prime, again the number is there, this is A triple prime ket A triple prime. All right, now this is equal to, again we know how to multiply this. All right, now this is a number, root 3 by 3 A prime is a number because A prime is the eigenvalue, which is a number. Oh, sorry, I missed the ket here, this is A double prime ket A double prime. Okay, all right, so this is a number, so we just can combine this bra with each of the bra here. Okay, I can combine bra A prime with ket A prime, I can combine bra A prime with ket A double prime, I can combine bra A prime with ket A triple prime, but only one of them is non-zero because of orthonormality. Okay, the non-zero combination is bra A prime ket A prime. Right, similarly, when I combine bra A prime with every ket in this on the right side, all right, what I get, the only non-zero value is bra A double prime ket A double prime. Okay, similarly, when I combine bra A triple prime with each of the kets here, right, what I get, the only non-zero value is bra A triple prime ket A triple prime. Okay, so let me first write the numbers together. This is equal to root 3 by 3 from here. Here also there's a root 3 by 3, that's root 3 by 3 square. Okay, there's the eigenvalue A prime, that's also a number, so I am writing all the numbers together, and I have got bra A prime ket A prime, which is equal to 1. Right, similarly I combine this with every term in here, the only non-zero value corresponds to bra A double prime ket A double prime. So let me write the numbers together first. So this is equal to 2 by 3 square and the eigenvalue A double prime, and then bra A double prime ket A double prime, which is equal to 1. Right, and from here I have a root 2 by 3. Here I have got a root 2 by 3 from here, so that becomes 2 by root 2 divided by 3 square. Okay, root 2 divided by 3 square, and the eigenvalue is also the A triple prime. Okay, and if I expand that, I should get the answer that we were talking about earlier. It's exactly the same thing. What is this? Is mod C1 square A prime plus mod C2 square modulus C2 square A2 A double prime plus modulus C3 square A triple prime, which is exactly the expression that we got before. Okay, so the answer here, if I do this thing, the answer is simply this. Let me write it here. It is 3 by 9. Okay, 3 by 9 A prime plus 4 by 9 A double prime plus 2 by 9 A triple prime. Okay, that's the average value or the expectation value of A. So this is how we do this thing. Alright, so we have seen what we mean by expectation value. This is the definition for expectation value, and if I do that, the final expression that I get is a weighted sum of the eigenvalues of A, right, of operator A. But it's a weighted sum. What's the weight? The weight is the probability. So you multiply each eigenvalue with its probability that's defined by quantum mechanics. So what I get here is, I am repeating what I said before, what I get here is actually A prime multiplied by probability of A prime. Okay, so it's a weighted sum of all the eigenvalues. Okay, plus A double prime multiplied by probability of A double prime plus A triple prime multiplied by probability of A triple prime, which is equal to A prime multiplied by quantum. The measurement theory of quantum mechanics tells me how to calculate the probability of A prime, which is equal to modulus of C1 square. Okay, this is A double prime modulus of C2 square plus a triple prime modulus of C3 square. So that's how we calculate the expectation value of an operator. I hope it is clear. I also hope that what we discussed in the measurement theory and when we defined expectation value, etc., I think these things become clear when we these things have become clear when we discussed this problem. All right, so let's move on to the next problem. This is the second problem. We are given the matrix representations of two kets, ket psi and ket phi. All right. All right. So ket psi is represented by the column matrix with entries 5i, 2, minus I, and ket phi is represented by column matrix with entries 3, 8i, and minus 9i. Okay. Now find the matrices representing ket psi star and bra psi. So sometimes this notation is used, right? If this is psi, okay, this is the matrix representing psi. What's psi star or ket psi star? Right? You just complex conjugate the entries here. So it's minus 5i, 2, and I. That's the meaning of the complex conjugate of the ket. All right. So this actually means the complex conjugate of the matrix that represents the ket. Right? But this notation is often used. We can write it like this. Right? Now, what's the bra psi? In order to find bra psi, what you do is you have to transpose ket psi and complex conjugate. All right, it's a transpose conjugate. So we get minus 5i, 2, and I. This is bra psi. Okay. Now the next question is ket psi normalized? Is ket psi normalized? If not, normalize it. So let's check if it's normalized first. We know that the matrix representation obeys. Okay, we have seen that the matrix representations obey the usual rules of multiplication. Right? We can find bra psi, ket psi by multiplying the corresponding matrices. Right? We have seen that the matrix multiplication rule works. So let's find the matrix corresponding to bra psi, which we already wrote. It's a transpose conjugate of ket psi. So that is minus 5i, 2, and I. Okay. What was ket psi? It's 5i, 2, minus I. So we multiply this. We know how to multiply a row matrix by a column matrix. Okay, we get minus 5i multiplied by 5i, which is equal to 25. Right? Because minus I multiplied by I is 1. Okay, plus 2 multiplied by 2, that is 4, and then I multiplied by minus I is 1. This is equal to 30. Right? So we see that bra psi ket psi is equal to 30, which means that it's not normalized. If it was normalized, we should have bra psi ket psi is equal to 1. Right? So now we need to normalize it. The second part of the other part of the second question is, if not, normalize it. How do we normalize it? How do we make sure that bra psi ket psi is equal to 30? Sorry, how do we make sure that we need to define a new ket psi tilde in such a way that bra psi tilde ket psi tilde is equal to 1. How do we make sure of this? Okay, how do we make sure? Okay, so I think we get an idea from here. Let's look at this. All right, we see that if I take bra psi ket psi divided by 30, right, this is equal to 1. This is equal to 1. Right, now I can write this as bra psi, or let me write this like this. This is 1 divided by square root of 30 bra psi, okay, multiplied by 1 divided by square root of 30 ket psi. Okay, I could write it like this. Okay, this is equal to 1. This is equal to 1. All right, so this means that 1 by square root of 30 multiplied by ket psi is normalized. This is a normalized set. This is normalized. Why? Because if I take the corresponding ket and if I take the corresponding bra, which is 1 by square root of 30 bra psi, multiply it with this ket, I get 1, which means that this is normalized. All right, so I can say that I have found the new normalized state psi tilde. This is equal to 1 by square root of 30 ket psi. Right? Or in general, what's the rule of normalizing? If psi is not normalized, right? If psi is not normalized, okay, I can define a normalized ket psi tilde, which is equal to ket psi divided by square root of bra psi ket psi. Okay, we saw that bra psi ket psi is 30. Right, so this rule gives me ket psi divided by, in this case, all right, if I am using this ket, this gives me ket psi divided by square root of 30. This now is a normalized state. Okay, all right. The next question is to find whether ket psi and ket phi are orthogonal. Right? If they are orthogonal, the combination, right? You have to take one. If you need to find two kets are orthogonal, you need to find the bra corresponding to one of them and combine with the other ket to see if it is 0. Okay, which means that we have to check whether bra psi ket phi is 0 or bra phi ket psi is equal to 0. Right? Both these conditions would mean that they are orthogonal. So let's check this. Let's check the second relation. Right? So let's find bra phi first. Bra phi is actually represented by 3 minus 8i and 9i. Sorry, I should have transposed it. So this is the row matrix 3 minus 8i and 9i. Okay, so what is bra phi ket psi? This is equal to 3 minus 8i 9i multiplied by 5i 2 minus I. This is the matrix that represents ket psi. This is the matrix that represents bra phi. Now we just have to multiply this and see if this is equal to 0. Let me write it here. This is equal to, right, 3 multiplied by 5i, that's 15i, minus 8i multiplied by 2, that's minus 16i. Is that correct? 15i minus 16i, and here I have got 9i multiplied by minus I. Okay, 9i multiplied by minus I. So 9i multiplied by minus I is plus 9. All right. So this is equal to 9 minus I. Right? This is the real part, 9 minus I. This is not equal to 0, which means that these kets are not orthogonal. Right? These kets are not orthogonal. All right. So we have seen that the inner product is a complex number in general. Right? We get some complex number, but this is not equal to 0, which means that these kets are not orthogonal. Right? Now, just for the sake of practice, let's also find. Here we have found bra phi ket psi. Let's now find bra psi ket phi. Right? Let's find bra psi ket phi. Right? Just for practice. All right? So let me write down the first result here. I have got bra phi ket psi is equal to 9 minus I. This is what we found here. All right? Let's find bra psi ket phi. Let me make some space here first. All right. Okay. So what's bra psi? It's the row matrix with entries minus 5i to I. Right? What is ket phi? I have got 3 minus 8i and sorry, it's 3 8i and minus 9i. Right? 3 8i and minus 9i. What is this? Minus 5i multiplied by 3, that is minus 15i plus 16i. All right? And I multiplied by minus 9i is plus 9. Right? What do I get? I get here 9 plus I, because 16 minus 15 is 1. So it's 9 plus I. Right? So we see here that we actually see here that bra phi ket psi or bracket phi psi is 9 minus I and bracket psi phi is equal to 9 plus I. This is exactly what we expected, because we have the rule bracket phi psi is equal to bracket psi phi star. Okay. Right? We know this rule. So we see that the rule works. Right? It works here. We found it in two different orders. We found bra phi ket psi, that's equal to 9 minus I, and we found bra psi ket phi, which is equal to 9 plus I, and this is the complex conjugate of bra phi ket psi. So we have verified that this works, at least in this case. Bra psi ket phi is equal to bra phi ket psi star. Okay. Here's another problem. A quantum state is given by ket psi is equal to root 2 by 3 phi 1, root 3 by 3 ket phi 2 plus 2 by 3 ket phi 3. Okay, and it's given that these eigenvalues, this phi 1, phi 2, phi 3 are eigenkets of an operator that's denoted by h. Okay, h phi 1 is equal to epsilon multiplied by phi 1. The eigenvalue equations are given. H phi 2 is equal to, it's given here, 2 epsilon multiplied by phi 2, and h phi 3 is given by 3 epsilon multiplied by phi 3. Okay, the eigenvalue equations are given. So what have we done here? We have expanded ket psi, right? Or the given expression is the expansion of ket psi in the basis of the eigenkets of an operator H, right? Basis of the eigenkets of operator H, right? Where H is the Hamiltonian operator, right? So it's given that H is the Hamiltonian operator, and later we'll see that Hamiltonian operator is the name of the operator that represents energy, right? Energy is an observable quantity. There's a Hermitian operator representing energy. It's called the Hamiltonian, right? Now I hope there's no surprise there because we have related Hamiltonian with energy even in classical mechanics, all right? So the operator representing energy is called as the Hamiltonian operator. Now calculate the probabilities of finding the particles in the state ket phi 1, ket phi 2, ket phi 3. Right? First, let's check whether the state is normalized. Right? First, let's check whether the state is normalized. Right? So in order to check this, what we need to do, just because this is an orthonormal basis, well, let's say that this is an orthonormal basis. Right? It's not explicitly stated here, so let's assume that it's an orthonormal basis. And if I do bracket of psi with itself, what I get is modulus C1 square plus modulus C2 square plus modulus C3 square. What is this? This is root 2 divided by 3 square plus root 3 divided by 3 square plus 2 divided by 3 square. What is this? Let me write it out. It's 2 divided by 9 plus 3 divided by 9 plus 4 divided by 9. Alright, which is equal to 9 by 9 and is 1. So the state is normalized. Alright, that's good. The state is normalized, which means that we can simply say that the expansion coefficient of each ket in here, right? Expansion coefficient of each ket can be directly equated to the probabilities, right? Can be directly equated to the probabilities. Okay. All right. Now calculate the probabilities of finding the particle in the states ket phi 1, ket phi 2, ket phi 3. All right. So the question I think is slightly inaccurate because this is the state of the system, right? This is the exact state of the system. So what we are calculating is if I measure H on this state, if I measure the energy on this state, all right, it will change to either ket phi 1 or ket phi 2 or ket phi 3, all right? It will change to either of these. It will change to one of the eigenkets of the operator H, all right? Now what we need to calculate is actually the probability that it will change to ket phi 1 or ket phi 2 or ket phi 3. Now since the state is normalized, we can write it like this. The probability that ket psi on a measurement of the energy changes to ket phi 1 is simply given by bra phi 1 ket psi modulus square of this. All right, what is this? This is simply the modulus square of the expansion coefficient here because of orthonormality. Okay, if I multiply by a bra phi 1 from here, all right, it will kill all these terms here. I get only bra phi 1 ket phi 1, which is equal to 1. All right, so this is bra phi 1 ket psi is square root of 2 by 3. If I find the modulus square of this, it's simply 2 divided by 9. Okay. Calculate the probability of finding the particle in the state ket phi 1, ket phi 2, ket phi 3, and the probability that ket psi changes under a measurement of energy into ket phi 2. All right, this is equal to, by the measurement theory, bra phi 2 ket psi modulus square. Okay, modulus square of bra phi 2 ket psi. This is equal to modulus square of this number, modulus C2 square if you like. This is equal to 3 divided by 9. Okay, similarly, the probability that psi changes under a measurement of Hamiltonian into state phi 3. Right, this is equal to modulus square of bra phi 3 ket psi. All right, mod square. This is equal to modulus C3 square, which is equal to 4 divided by 9. All right, so we have found the first, we have solved the first part of the problem. We have found the probabilities that the state changes to ket phi 1, ket phi 2 or ket phi 3. Now find the average energy of the system. Now the next part of the question, the second question is find the average energy of the system. All right, now we know how to find the average energy. All right, we know how to find the average energy. We can find the average energy like this. It is bra psi h ket psi. This is known as the expectation value or the average value. All right, but now since we know that we have said that this is an orthonormal basis, etc., this simply can be written by as the eigenvalue. Let's denote the eigenvalues. Let me write the eigenvalues as E1, E2 and E3. All right, so it's P of E1 multiplied by E1 plus P of E2 multiplied by E2 plus P of E3. What's P? P is the probability, right? P of E1 is the probability for measuring energy E1 multiplied by E3. All right. Now, what are E1, E2, E3? These are the possible measurement outcomes, and these are given in the question, right? Because the eigenvalues are given as H51 is epsilon phi 1, H52 is 2 epsilon phi 2, H53 is 3 epsilon phi 3. So the eigenvalues are, we have got the first eigenvalue is epsilon, the second eigenvalue is 2 epsilon, and the third eigenvalue is 3 epsilon. Right? So I just substitute this here. And what's probability of E1? Probability of E1 is just the modulus square of this expansion coefficient. So what do I have here? This is 2 divided by 9. Okay, by the probability interpretation. Right? The expansion coefficient square gives you the probability for measuring the corresponding eigenvalue. Okay, so it's 2 by 9 multiplied by epsilon plus 3 by 9 multiplied by 2 epsilon plus what's P of E3? It's 4 divided by 9 multiplied by 3 epsilon. I just add all this, so there's a 9 common in the denominator. Okay, let me write it here. I've got a 9 in the denominator. This is 2 epsilon plus 6 epsilon plus 12 epsilon. Right, so that is 20 epsilon. I hope I'm not wrong here. It's 2 epsilon plus 6 epsilon, right? There's a multiplication sign here. 2 epsilon plus 6 epsilon is 8 epsilon. 8 epsilon plus 12 epsilon is 20 epsilon, right? So what's the average value or the expectation value of H? It is 20 epsilon divided by 9, all right? It's 20 epsilon divided by 9, all right? All right, the next question is, consider a state ket psi is equal to 1 by root 2 ket phi 1 plus 1 by root 5 ket phi 2 plus 1 by root 10 ket phi 3. This is the state is given, right, which is given in terms of three orthonormal eigenstates, ket phi 1, ket phi 2 and ket phi 3 of an operator B. Okay, it's not mentioned what operator this is, it's just some operator B such that B phi n is equal to n square phi n. So the eigenvalue equation is also given, which means that B phi 1 is equal to 1 square phi 1 or 1 phi 1. B phi 2 is B phi 2 is 2 phi 2, okay, and B phi 3 is 3 phi 3. Right, so that's these are the eigenvalue equations. Now the question is to find the expectation value of B. Right, so we have to be a little bit careful here because we know the definition for expectation value in the state psi is ket psi, sorry, bra psi B ket psi, right? But this is true only if this is normalized, all right? Bra psi ket psi is normalized, sorry. Bra psi ket psi is 1. Okay, or ket psi is normalized. Now here we have to check whether ket psi is normalized. So let's find bra psi ket psi. That's equal to 1 by 2 plus 1 by 5 plus 1 by 10, which is equal to, you can take 10 as the LCM, 5 plus 2 plus 1. So that's actually equal to 8 by 10, or this is equal to 4 divided by 5. So we see that it's not normalized. Okay, but this result, this works only for normalized psi. Okay? So actually what we do is that if the state is not normalized, we take a normalized state, square root of bra psi ket psi. We take a normalized state. Okay, then we can find the expectation value. Okay, expectation value of B is equal to bra psi tilde B ket psi tilde. Right, since now it's normalized, this result will work. Right, but what is, so this is the normalized state. Let's say that this is the normalized state, bra psi, sorry, ket psi tilde. Okay, so this means that bra psi tilde is equal to 1 by, this is a real number, so it's 1 by square root of bra psi ket psi bra psi. Right, so this is bra psi tilde because ket psi tilde is given like this, a normalized state, ket psi tilde is given like this. So bra psi tilde is bra psi divided by, or 1 by square root of bracket psi psi multiplied by bra psi. This is the corresponding bra. Okay, this means that bra psi tilde B ket psi tilde is actually equal to, what's bra psi tilde? It's 1 by square root of bra psi ket psi, all right, and bra psi. Right, so this is what is this? This is brass psi tilde, normalized state. And then I've got the operator B. And instead of ket psi tilde, what do I write? It's ket psi divided by square root of brass psi ket psi. All right. Now this 1 by square root of brass psi ket psi is a number. Right? So it can travel past any bra or ket. So we can combine the numbers together. So we see that there's a square root of square root of bracket psi psi here. There's a square root of bracket psi psi here. So we can combine that in, and you get psi tilde b psi tilde is equal to 1 by brass psi ket psi. Okay? Because of the square root here and here, the square root vanishes. I multiply both of them, and then I have psi b psi. This is how we find the expectation values. All right. So this means that in general, right? In general, if you want to find the expectation value of B, what you need to do is this actually, right? In general, the expectation value of B is given by bar psi B ket psi divided by bar psi ket psi. Okay, this is the rule. This is the general rule for finding the expectation value. Okay. Now, if it's normalized, fine. This factor is 1, it's fine. Otherwise, we have to divide it by this. Right? So what we need is we can find bar psi b ket psi and divide it by this number, bracket psi psi. We found that bracket psi psi, I think it was 4 by 5. Right? So we'll leave this 4 by 5 here. We can first calculate the numerator and finally divide it by 4 divided by 5. Okay, that's what you have to do. I'll leave it as an exercise for you. Right? Again, you can find the numerator easily. Right? You can find the numerator easily. The state is given here. So you just find, and we know the eigenvalue equation. Right? B phi n is n square phi n. Use the eigenvalue equation, find the numerator here, and divide it by this factor. That will give you the expectation value. Right? So I leave the rest of it as an exercise for you to complete. Right? Okay, with that, we'll complete this discussion of problems. Thank you.